Today I'm going to be talking about activation energy. Have you guys had those days where you just don't want to get out of bed, but you need to muster enough energy to get over that hump and go about your day? Whether it be coffee or ringing the alarm to give you that extra push, once you get past that hump, you are ready to go. That hump is referred to as the activation energy in a chemical reaction. The activation energy is the amount of energy needed for a chemical reaction to occur. More specifically, it's the amount of energy required for reactants to get to that transition state or activated complex, which you can see right here. It's the top of the peaks. At this state, the bonds are partially broken and partially formed. The activation complex has a very high level of energy compared to the products and the reactants. It's also unstable, so the reaction will want to proceed quickly once it hits that point. The larger the activation energy, the more difficult it also will be for the reaction to occur. So you can provide extra energy by increasing the temperature, which increases the average kinetic energy of the molecules. You can also add an enzyme or a catalyst, which can be used to lower the activation energy, which you can see here with the blue curve, which is the activation energy with a catalyst. As an example from earlier, coffee can be the catalyst to help you get through your day. The Arrhenius equation can be used to calculate activation energy. It is K equals A times e to the power of EA over RT, where A is the frequency factor, K is the rate constant, which is calculated experimentally, EA is the activation energy, R is the gas constant, and T is the temperature in Kelvin. The activation energy can also be found graphically when the natural log of K, or the rate constant, is compared to the inverse temperature in Kelvin. It's in the form of y equals mx plus b, where y is the natural log of K, the slope, or m, is the activation energy over the gas constant, x is the inverse of T, or temperature, and b, or the y-intercept, is the natural log of A. And you can find here that the shorthand equations for activation energy and frequency rate. There is also an equation to use called a two-point Arrhenius equation when you are given two sets of data, such as two rate constants or two temperatures, and you need to find one or the other, etc. Now let's do a problem together. Determine the activation energy in kilojoules for H2 plus 2ICl, which turns into 2HCl plus iodide gas. If the rate constant is 2.75 times 10 to the negative 8 at 327 degrees Celsius and 1.95 times 10 to the negative 7 at 527 degrees Celsius. Here you would use a two-point Arrhenius equation, and once it's solved, the activation energy is 39.1 kilojoules per mole. And that is my flipped classroom presentation on activation energy.